All right, so let's do a few more examples, and then I'm going to let you practice for the rest of class on this. Hopefully you're starting to feel a little more comfortable with these, right?
Yeah.
And remember your test on Thursday is all of them. I want to actually go back to the one we did yesterday in class.
Which one, number 2?
The one I told you to finish. I think it may have been number 2.
Yeah.
So it was the integral of x cubed plus 1 over x squared minus 4, right? And so yesterday when we did this, we got this to the point that we had the integral of x dx plus the integral of 4x over x squared minus 4 dx plus the integral of 1 over x squared minus 4. We had done this one already with u sub, right? And we found out what that one is. So this one I had you doing it with trig sub. So we did it, we set up our triangle with our radical on the opposite side, so x squared minus 4 with x on the hypotenuse and 2 on the adjacent side. We did all that and we ended up with the integral of secant theta over 2 tangent theta d theta, right? And I think that's the point where I stopped at on this one yesterday and told you to finish it, right?
Right.
So, if you finish that, what did you end up with for that antiderivative? All right. Raise your hand if you finished it. So what you get, Kyle?
1/2 x squared plus 2 natural log absolute value of x squared minus 4 minus 1/2 natural log absolute value of cosecant theta plus cotangent theta plus c.
But be careful. What do you got to do with those cosecant and cotangent thetas? Got to convert them back to x, right? So let's just focus on this part, right? So this part, you ended up with negative 1/2 natural log absolute value cosecant theta plus cotangent theta, right? So the reason why is, remember the hint I told you yesterday, take that back to sines and cosines and simplify stuff, right? It simplifies rather nicely to end up becoming the integral of 1/2 of the integral of cosecant theta. When you take that to back to sines and cosines and simplify. So that's how you get to here. Then translate it back. So read off your right triangle. You should be pretty comfortable doing that at this point, right? We've been doing it for a while now. So you end up with 1/2 absolute natural log of absolute value of x plus 2 over square root of x squared minus 4 plus c. Whenever you read off that right triangle and then simplify that radical, or that absolute value. Because you end up with x over square root of x squared minus 4 plus 2 over square root of x squared minus 4 for the cosecant theta, cotangent theta, respectively. So you end up with that. And so plug back in, you end up with, after all that work that we did yesterday and then some other work, you end up with this. I'm jumping ahead a step. Let me get back even further. Are you done?
You can simplify it.
You can simplify that. How can you simplify that, Logan?
The natural logs, natural log minus natural log is something you can end up being that as a division, but you need to make sure that the constants are the same, correct or no?
So you got to bring these constants in, right?
Yeah.
So bring the constants in, then you can do exactly what you're saying. Subtract them. Make a division. So if we do that, 1/2 x squared plus natural log of x squared minus 4 squared, right? Here, so I'm bringing that in as a squared. Since it's something squared, we can drop the absolute values, right? Although, to be helpful, I'm actually going to write it like this, just so that it stays in an absolute value, because we can't say anything about this one's absolute value, right? Or can we? Just to be safe, we'll keep the absolute value. Right, even though we know we can technically drop it here, but for simplification with this piece's purpose, we're gonna keep it. Minus natural log of the absolute value of the square root of x plus 2 over square root of x squared minus 4, right? Plus c. And now we can combine, make that division. Has that really made it cleaner?
No.
No, but let's keep going with it, right?
Yeah.
There's a reason why I'm doing this. What would you do?
So can you take it to the point where you take the square root of the square root of x squared minus 4, which is then just the x squared minus 4, and then you multiply it by
Well, is the square root of the square root of x squared minus 4 x squared minus 4? What's the square root of the square root? Fourth root of it, right?
Yeah.
You're on the right track though with doing
One
that.
half.
You are on the right track with doing that though, Logan. So 1/2 x squared plus natural log absolute value x squared minus 4 squared. So split that square root into the numerator and denominator, right? So over square root of x plus 2 over fourth root x squared minus 4. Good.
And then can you take the denominator of the denominator and multiply by the numerator?
So in other words, can you do fractional division? The answer is yes, right? So that's technically over 1, right?
Yeah.
So there you go. So now multiply by the reciprocal of this denominator, right? So you end up 1/2 x squared plus natural log absolute value of x squared minus 4 squared over 1 technically times fourth root x squared minus 4 over square root of x plus 2 plus c. Okay. So now what?
So you can reduce the powers, right? The square times the fourth root.
Mm-hmm.
And does that bring it back to the square root or no?
You tell me.
1 over 4
So what do you do with their powers here? You add them, right? So what's 2 plus 1/4?
5/4.
Yeah, 5/4.
5/4. You sure?
9/4.
9/4, right? So you end up with natural log absolute value x squared minus 4 to the 9/4 over square root of x plus 2. Are you done?
Could you put the exponent in?
What do you mean?
Like the 9/4, like x cubed times 9/4, -4 times 9/4.
Nope.
Okay.
Can't do that. That is not a valid mathematical property. Since it's a difference, right? If it were just multiplication in here, yes, you could do that, but not for subtraction. All right, even better. Think a little more simply. Right? Factor. X squared minus 4, you should be able to factor all night long, right? To give you x plus 2, x minus 2. So now you've got that product raised to the 9/4, and can bring that 9/4 in now. All right? So now, you have that. And now you can combine those two. So you finally end up with a final answer of 1/2 x squared plus, and I'm actually going to do a few steps at once here, so plus 9/4 x minus 2, or natural log absolute value of x minus 2, plus 7/4 natural log absolute value x plus 2 plus c, once you do all of that. So 9/4 minus 1/2, so 9/4 minus 2/4, right, gives you the 7/4 natural log absolute value x plus 2, and then that's already the 9/4 natural log absolute value x minus 2. And I just split them back out since that would have then been a product inside the natural log, made it into the sum. Yeah.
Given if this was a definite convergent integral, could we just take it from where we finally get to C, where we get all the integrals out right there?
Yes. I thought so. Yeah. So definite integrals, if this were definite, at this point, you would sub in, right? Instead of having plus C. So, the reason I went back and showed you the answer to this one after I said finish it last night, because remember I said you could do this with partial fractions, right? So, because remember, I said split this up yesterday, right? And we split it up like that. What if, instead of splitting it up, what if I did it like this? So we got the integral, and what we started with was x cubed plus 1 over x squared minus 4. And so we did our long division, and we ended up with the integral of x dx plus this technically was our remainder, right? So that was the point where we split it up yesterday to avoid partial fractions. We split it up yesterday into two more separate integrals to avoid partial fractions. But what if instead of splitting this up, we tried partial fractions? So let's try to split up 4x plus 1 over x squared minus 4 using partial fractions. So that is 4x plus 1 over, what's x squared minus 4 factor as? Good. So then what am I going to have on the right-hand side now?
A over x minus 2, B over x plus 2.
Good. So then multiply both sides by my common denominator, and what do I get?
4x plus 1 equals
AX plus 2. AX minus 2.
Good.
Oh,
Right?
plug in -2.
So let x equal -2, so that gives -a plus 1 equals a -2 plus 2 is 0, b -4. So then we get b is 7/4, right? And let x equal +2, so 9 equals 4a. So a is 9/4. And so then we still split this up, right? So we end up with 9/4 over x minus 2 plus 7/4 over x plus 2. I'm going to skip a few steps that you should not skip when you're writing it out, right? So we end up with plus 9/4 1 over x plus 2, or sorry, x minus 2. I've got them written backwards down here, so that's why I'm like, whoa. All right, so 9/4 over x minus 2 dx minus the integral minus 7/4 of the integral 1 over x plus 2 dx, right? And now u sub u equals x minus 2, u sub u equals x plus 2, so 2 u subs later, you end up with 1/2 x squared plus 9/4 natural log absolute value x minus 2 plus plus 7/4 natural log absolute value of x plus 2 plus c. So all of that to get there, or a couple of u-subs. With partial fractions, right? So, the reason I did that, because I wanted you to see, you don't always have to do partial fractions. You don't always have to. But sometimes the partial fractions make it easier. They can make it easier. Questions? Yeah.
So you can have repeated linear factors, but you couldn't have like x plus 2 to 1/2 use partial fractions. That would require trig stuff. I guess is the possibility to use partial fractions on something like that?
I would. I'm not going to say it's not a possibility, but it's way beyond the scope of our class. I'd keep it simple and stick with the trig sum on that one. Other questions? Let's do a couple more of these. Well, let me ask you this. How are you feeling? Do you want to see a couple more examples, or are you ready, want to try some?
Can you do one that ends up being like quadratic, like instead of just the same linear?
Yeah.
Yeah.
Yeah, absolutely. How about, where's the remote? So how about this one? Integral of 18 over x plus 3 times x squared plus 9 dx.
Cool. So you can do you can have that 18 over x plus 3 and x squared plus 9 equals a over x plus 3 plus bx plus c over x squared plus 9.
Good.
And then multiply by common denominator, etc.
All right.
-3. Plug in that.
Mm-hmm. So start with your simple clearing out stuff, right? So let x equal -3. So 18 equals a times -3 squared plus 9. This is all 0, right? Because this is -3 plus 3.
Oh, never mind.
Doesn't even matter that you have to put the -3 in there, right? Because it still times that 0. The beauty of those simple values. So 18 equals 18a. A is 1. All right. So now you've got a couple choices you can make. You're at a crossroads now. So you can pick two other random values of x. That'll be nice, easy numbers to substitute in. Maybe 0 and 1. All right. You can pick them and get a system of equations. Or you can plug in the one you know. Either way, I'd plug in the one I know. And then equate your coefficients. My recommendation would be plug in the one you know and equate your coefficients. It's not to say you won't still end up with a system of equations, because you might. But usually, it's just a little bit less. It's a little more tedious, but it's a little less work. And also, it's going to be good practice for those of you going on differential equations when you start trying to solve differential equations using the method of undetermined coefficients. So it's also good practice for those of you going on 285. That's another reason why. But either way, plug in a equals 1, right? So we now have 18 equals x squared plus 9 plus bx plus c times x plus 3. And so you have a choice. Let's just go ahead and do this by equating our coefficients, right? Because this isn't hard to multiply out and then set things equal to each other. So 18 equals x squared plus 9 plus bx squared plus cx plus 3bx plus 3c, right? Whenever I pull out bx plus c times x plus 3. Still with me?
Yeah, so you just, instead of multiplying out directly and then rearranging it, you just multiplied it, but just kept it in a proper
Yep.
arrangement of x
So I
squared
just
and
went
x.
straight through. All I did literally straight through, dropped these parentheses, pulled that out.
Yeah.
That's it. So now I'm going to rearrange it and group my squares together, my linears together, and my constants together. So x squared, so 1 plus b x squared, right? Plus, you tell me, what's my linear piece going to be? Something x.
C plus 3b.
Mm-hmm. And then my constant?
3C.
What else?
And a 9.
All right, so now we have constant, or we have 3 different coefficients, right? Question.
Would it be easier to get the terms without capital variables on the other side before you do that? So you just have bx equals, and then you pair that with x squared on the other side, and then b would just equal -1. Would that be easier?
Say that again?
So getting the terms without capital variables, so x
Okay.
squared plus 9, you subtract them over.
Okay, yeah, you can do that.
Okay.
You can do that. It really, I'm not going to say it's necessarily easier, because you're still going to end up doing the same math. It's really just whichever way you want to do it. This is just happens to be the way I learned how to do it, and so old habits die hard. But no, there's absolutely nothing wrong with that. If you want to move the terms that don't have your unknowns to the other side of the equation, you can absolutely do that. All right. So either way, though, 1 plus b then equals what?
0.
0. So now b is -1, right? Which you get the same thing if you move the x squared over, right? You get -x squared equals bx squared. So same thing. And then here, well, 3, I know what b is now, so that's -3, right? Plus c equals 0. So c equals 3. And we don't even care here, right?
We got what we need?
We got what we need. Here, you can just use it to check yourself, right? 3 times 3 plus 9 is 18, right?
Yeah.
So we know that c's right. But either way, you now have your a, b, and c. And so you're good. All right. Questions? So then, what's this integral become? The integral of what?
1 over x plus 3 plus the integral of negative x over x squared plus 9. For b is x
B is
-1
negative
plus
one,
negative
right?
x plus the integral of 3 over x squared plus 9. Or you can bring the 3 on the outside and put 1 over blank. It makes it easier.
Good. And you can also bring this negative out, right?
Sure.
It's not much difference, but hey, we're pulling stuff out. Let's pull it out, make it a little bit easier, right? All right, how would you do this one?
Use of
Yeah.
With u equal to?
X plus 3.
Good.
do you use
Here,
Yeah, what would you do?
You said
Use of.
X squared plus 9.
here, what would you do?
Trig sub.
Or,
Arctan or
that is your
Yeah,
arctangent one,
'cause
right?
That's an a squared plus a.
That's
u
a
squared.
squared plus u squared. If you know, so that's why I said that you don't have to memorize those inverse trig function antiderivatives, right?
Yeah.
But if you do, it gets you out of having to do trig sub here.
Yeah.
So either trig sub,
I wonder where your bias is.
well, actually, I love trig sub, so,
Oh, okay.
but it's more work.
Track it.
Right?
Yeah. And one thing, just wondering when doing the trig antiderivative, u is always equated to x and a is equated to the constant.
U is going to be the piece that has the x in it.
Okay.
A is going to be the part that has the number in it. Yes.
Okay, cool.
Yes. So if we did that, blah blah blah, you do the work, because at this point you should be more than comfortable doing U subs, right? And if you remember your inverse trig antiderivative formulas, this should be a piece of cake. And if not, well, if you know how to do trig sub, this isn't a bad trig sub one.
Complicated at all, really.
Exactly. So you end up then with what? Natural log absolute value x plus 3 minus natural log minus
1/2.
1/2 natural log absolute value. Or do I need absolute value here?
Nope, no, because it's squared.
No, because it's x squared plus 9, right? So natural log x squared plus 9. And then this one is what?
The
3, 1 over a, arctan u over a plus c, right?
So 1/3 arctangent x over 3.
There you go.
Professor, you didn't do all the u subs for that.
I
You
know.
write all your work.
That's why I put the ellipses here.
But you do that for our sake.
I get to wave the magic wand.
Yeah.
Graduate school and privilege.
You get to do the work. Because you should be comfortable doing that work by now.
That's
That's the medium talk too.
Yeah. When we're like right there and we can just put the natural log, it's always like, okay, what space am I gonna take up doing this real quick? So then just bring it back.
Yes. All right. Any others you want to see? Yeah, right?
just shows how you factor the denominator on problem 19.
Problem 19. All right. So you've got a denominator of x cubed minus x squared plus x plus 3. You got a couple different ways you can do this. If you have 4 terms, first thing I would try is factor by grouping. If that'll work, great. Factor it, Merry Christmas. I think factor by grouping works on one of the example problems I gave you, or the extra problems I gave you, I should say, on the homework sheet. Or no, I factored all of those. But either way, it must have been one of the web assigned ones that factor by grouping works on. So if factor by grouping works, great, Merry Christmas. Factor by grouping doesn't work here. Because if I pull out an x squared, I end up with x minus 1, not x plus 3, right? So factor by grouping fails. So then, what do you need? To be able to factor it, you need 1 0, right? You need one value that's going to make this 0. Use your graphing calculator. Graph it and find a 0, right? On the homework, you have that privilege. On test, you won't, so I won't give you one like that where you have to find a 0. I'll give it to you already factored. So, everyone remember how to find the zeros with the graphing calculator?
It's been a
Yes.
long time, but yeah.
Alright, so I'll show you, and hopefully not make this recording stuff.